Well, sorry about the last class. It was an emergency. I could not manage, but I think let's just go through. So now, in the last class, we talked about the momentum integral condition for the wake, and we found out that there was a quantity which was an integral quantity, rho times capital U times U minus U infinity, average wherever U was there, dy from minus infinity to infinity. That quantity did not change as a function of the downstream distance x. Okay. So now we will talk of using these concepts to develop the turbulent wake, and the first concept we have here is self-preservation. And self-preservation, or sometimes we also refer to this as a self-similar profile. So suppose we have a quantity q, which is a function of x and y. So this is a dependent variable. X and y are what we term as the independent variables. So if we can write let there be some scaling of q being done by a quantity called q0. Now this q0 could be q, now, and this is a function of x. So that means it could be the value of q at y is equal to 0, or it could be an integrated q over dy, and then you divide it by the lateral width. So that could be q0x. So there's some sort of scaling is being done. And you can also think of this as that we are non-dimensionalizing q, because q0 will have the same dimension as q. So q hat, that means that q can be expressed as q hat of eta, and eta now, or eta is a non-dimensional y. That means eta is written as y divided by some function of x. So effectively what you are saying is that the variable, instead of changing with both x and y, is a function of a single variable eta, and this eta in turn depends on both y and x. And typically if this happens, then we say that we have a similar form for q. The solution for q is similar. Yeah. Now this delta of x, in terms of when we use it in Baudelaire, it becomes the Baudelaire thickness, but in general it is some function of x.
So sir, it can be like delta by y also.
It can be y by x, it can be y by x to the power of half, x to the power of 1/3. Typically this delta function is taken as some power of x, and then we try to put it in the equations to see what are the conditions for getting the self-similar profile. So eventually when you do this exercise, the equation for q, which was q of x comma y, will become an ordinary differential equation for q hat of eta.
So can we say that we are doing essentially parameterization?
we are doing some sort of parameterization, but the aim of that is to convert the partial differential equation to an ordinary differential equation. Okay.
So that all the y's and x's are
All the y's and x's, instead of being y and x, they come in the form of eta. That is the basic purpose of all these self-similar things, and what this will show is that as the flow evolves with x, then all these self-similar profiles for all values of y and x will be a single curve, only a function of eta, not of y or x separately. So, this is the whole purpose of or this is what we call as the similarity profile or self-preservation. So, now in the context of, and so let me, so q hat is just a function of one independent variable eta, which in turn depends on both y and x. And to get to the forms of this, we will have to revert back to our equations. Are determined eventually we are left okay. So now let us look at this in the context of a turbulent wake. So did I say no? So now in a wake, if we non-dimensionalize the mean velocity and we do it as u0 minus u hat divided by us, which is the velocity at the center line. So, this is just a non-dimensional defect. Okay. So, this we will find will be a function of y by L. Y is this distance from the axis, L is the some sort of non-dimensionalizing length which we have not yet defined how it changes. L upon capital L, the place where you are, this capital L represents the x distance. L US upon u is the Reynolds number, and this US upon u naught, how strong is the outer flow compared to the defect. So, it is a function of all these variables. Now, the approximations are made for fully developed wake, which implies small l upon capital L goes to 0, L US upon nu, fully developed turbulent wake, Reynolds number is large, and in this limit US upon U0 will tend to 0. So therefore, what we are assuming, and this is basically in line with the self-similarity profile argument, U0 minus U upon S is just a function of Y by L.
Correct me if I'm wrong, but isn't smaller than this? So if my wake is like this, so how much length is
Yeah.
that?
Yes.
This is the capital.
Huh. L is, capital L is the downstream distance at which you have the wake. So it's some sort of non-dimensionalization. So this distance is some representative. We'll define what is small l or exact definition, but it represents this height, and this is capital L. So once we are talking of fully developed, we are sufficiently downstream. So capital L is large. So the idealization becomes infinity. That L, capital L upon small l is infinite. It's an idealization. Of course, it may be large, but so under those conditions, that means in this region we will not expect a self-similar solution.
हाँ, so this should tend to 0.
नहीं Reynolds number नहीं क्योंकि L will be small, but Reynolds number तो large होगा ही. Turbulent flow है तो nu is very small.
So that's fair, but US is also like finite. When U is also
हाँ.
pressurized and small.
So how we can
See, we are talking of
by the scale, like for example, if L is 0, I mean
L, US and nu. So yeah, no, but this is basically again in the limit that we have large Reynolds number. Reynolds number is large. L and US may be small, but the Reynolds number overall is large. So that is what we are saying, that U minus capital U by US is just a function of, or you could think of that we are trying to now find a self-similar solution of the form Y by L. So we are dropping out the other variables. See, again, this is in some sense a hand-waving argument, I agree.
so we are just considering turbulent, so that's why
Yeah. So that we are saying RE has to be large enough. RE has to be large enough, otherwise the flow will not be done. Okay. And L is L of X. Now, since we are referring to velocity differences, we will assume the form of U0 minus mean of U will not change. Now in wakes, U prime RMS is of the order of US. So we will expect, and once again this is based on the Reynolds stress terms will scale like US square, and this will also be just a function of Y by L. So we are, in some sense you can also think we are imposing this self-similarity solution. So basically we have to find the form of mean U and find the form of Reynolds stresses, because these are the two terms which appear in our equations. So this form we are assuming that they are just a function of eta, or in fact in the book he has used the symbol zeta for Y by L, so we will use that. So these are the two forms. And this 1 and 2, and as I said, these form the self-preservation hypothesis. So the velocity defect, which is u0 minus mean of u, and the Reynolds stress are treated invariant with respect to x if they are expressed in terms of local length scale L and local velocity u sub s. So this is what the self-preservation hypothesis means, that they will not depend in, see x, of course the x comes through L, but not directly as a function. So invariant with respect to x means that of course they depend in terms of L and US. So these are the two scales on which they depend. Now we define zeta is equal to y by L. So therefore, partial zeta by partial x will be equal to minus y by L square into dl by dx, and this we write it as, what we are trying to do is we are trying to remove all y's, writing everything in terms of zeta and x. This is what we do in self-similarity and feed that back in the equation. So we'll need the derivative of zeta, so that's why we are doing this. And similarly, partial zeta by partial y will be equal to 1 over L. Now, let us look at the various terms. u0 minus mean of u, we have written it as us times f of zeta. This was equation 1. u0 minus u by us is equal to this. So now du by dx can be written as minus dus by dx times f of zeta minus us times df by d zeta times d zeta by dx, which is minus zeta upon L dl upon dx. You can call it 3, it's basically rewriting 1. 1 was just writing US here. So that's why I've written it as 1 so that you don't get confused. That it's coming from 1. Maybe you can call it 1 star if you want. And now I'm trying to calculate what is the d by dx of this. Du by dx will be given in this way. So this can be written as minus dus by dx times f plus us f prime zeta by L dl by dx. This is what we typically do when we do the self-similar analysis, that we take each of these terms and write them in terms of zeta and the derivative with respect to x now, because y's will be going away. In some sense, we are replacing y by zeta, if you can think of it, in the equation. And then we have the second term, which was term number 2, was u prime v prime, and this was equal to minus of us square times g of zeta. Now explicitly I will not write zeta, and wherever the derivative comes I will put it as prime, where prime means only with respect to zeta, total derivative. There is no partial derivative in prime. So this is u prime v prime is written like this, and in the equation we had partial u prime v prime by partial y. So this will become equal to minus us square, us is only a function of x, so minus ux square times, how will I differentiate? Let's try to do this. Exercise once, us is only a function of x, so this does not, when I take, now how do I differentiate this with y?
Delta by del y.
First g dash theta, then delta.
So g is only a function of zeta, so first g prime zeta times partial zeta by partial y. Okay, that is what I've done earlier also, but I didn't go through it. But this, so derivative of g of zeta with respect to y will be derivative of j with respect to zeta times partial zeta by partial y. And the same thing we did here, derivative of zeta with respect to x. So this became, for example, this f became f prime times partial zeta by partial x.
So this is f prime of this, or is it f prime times this?
Times this.
Because of the bracket it's looking. I was a bit confused.
Okay, no, it's f prime times. That's why in the second step I've made it explicitly clear. Okay. Yeah, okay, you could have been. But f prime is always, so minus us square times g prime times partial zeta by partial y is 1 over L. Now, the x momentum equation was u0 du by dx so this equation becomes u0 times minus dus by dx times f plus us times f prime times zeta by L dl by dx minus us square g prime upon L is equal to 0. And what we do is we divide everywhere by us square upon L. So divide by us square upon L. Why do we divide by us square upon L? Because this term is g prime, so we want to keep at least one term only with g and eta. So everything else will have a coefficient along with f and f primes, etc. sitting along. So when I divide by us square upon L, so this becomes equal to minus u0 L upon us square times the first term is dus by dx times f plus there's a u0 outside, so u0 and then we divide by us square, so we get 1 us here times dl by dx zeta times f prime, this is equal to g prime. So the L and L cancel out and we are left with u0 comes from there, we divide by us square, so us comes here and then f prime zeta and then L goes away and dl by dx. This must be equal to g prime. So this is basically the momentum equation for the self-preserved quantity. Now, if we have self-preservation and we also assume 0 is equal to constant, we are assuming this wake, there is no pressure effect outside the bound, outside the wake, so therefore u0 is a constant. So this we had also assumed earlier. So if u0 is equal to constant, then what happens is all coefficients, if self-preservation has to be there, all coefficients must be constant. So this implies condition A will become L upon US square dus by dx is equal to constant K1, and the condition B will become 1 upon US dl upon dx is equal to another constant K2. Okay. So now we put L goes like x to the power of n in this equation. So this will give us US will go like x to the power of n minus 1. We look at equation number B. So if L goes like x to the power of n, then dl by dx will go like n times x to the power of n minus 1. So US also has to then go like x to the power of n minus 1. And if you put in the first equation, you will not get anything else. It will again give you the same thing. So we have one relation between how L and US go, but we don't have a second relation from these equations, because both of them give the same condition for self-similarity. No, because we want to find the values of how is L going with x and how is US going with x. So to determine the value of n. Okay, because we need one more equation which will relate L n, which will give us the value of n. Okay. So now from here what we get is we need a second equation or a condition to find n. And for this we use the momentum condition, that capital M, or the momentum, I can probably call it the momentum integral condition, that capital M is a constant. Now what we had defined was minus m upon rho was integral from minus infinity to infinity u0 minus mean of u times mean of u dy. So here now we substitute. Now if you recall, a similar exercise would have been done when you did your laminar boundary layers. You got it as x to the power y by x to the power of half. So there what do you do in laminar boundary layers? If you recall, we equate the convective term with the term on the this thing, with the viscous term, the dominant viscous term. That gives us one condition. And the second condition comes from the boundary condition that u must be equal to capital U, a constant, as eta goes to infinity. So and it is 0 at y is equal to 0. So there we use the boundary condition. Now in terms of wake, the flow does not have any boundary. If you look at it, we are in this part of the wake. There is no physical boundary where you can use a no slip condition. So here that condition comes from the momentum condition. And in fact, if you do, I don't know, have you seen laminar wakes or laminar jets in the course, in any other course? तुम्हारे को उसमें 391 you are not doing, you are in नहीं you are not, तो ये एडवांस फ्लूइड्स में नहीं कराई थी जेट्स वगैरह? नहीं, बाउंड्री लेयर तो कराया होगा, जेट्स नहीं कराते प्रॉब्ली. ओके, so jets maybe if need be I will do it, the laminar jet if I have to do. When I do the jets, I will, इसके बाद I will just come to jets and I will first do the laminar jet and then show the difference between the turbulent jet and the laminar jet. How do we do it? So, I think that is what I am going to do. So, this is what we have, this is equal to, so we substitute this in the above equation. So, what we get is, so u0 minus u is like this, and mean of u is equal to u0 minus us times f of zeta. So, when I put this in, and then dy will become L times d zeta. So, minus m over rho is equal to u0 times u0 minus u. So, the first term multiplied by, so I have us times f of zeta, I have to multiply these two terms. us times f of zeta multiplied by u0 minus us times f of zeta. So, the first term will be us u0 f of zeta, and the second term will be us square f square, isn't it? So, let us see. So, the first term becomes equal to u0 us times L integral of minus infinity to infinity f of zeta d zeta, and the second term will become minus us square L integral from minus infinity to infinity f square zeta d zeta. Just go through these steps carefully as you see. So, all I have done is I am replacing everything with f. Is that fine? Now, this term is us square L, this is u0 us L. Which term has a bigger order of magnitude? See, we are assuming f is a normalized term. So, integral f of zeta or integral f square, everything will be in the range of 1 or 2 or 3. Now, the coefficient here is us square, and the coefficient of the first term is u0 us. So, which will be bigger? u0 us, because u0 is much bigger. us is just a defect. Okay? So, when we look at these two terms, so what we have is us square will be much less than u0 us, and this will imply that the second term is negligible. So, therefore, what we have is minus m upon rho is equal to u0 us L integral from minus infinity to infinity f of zeta d zeta, and this is also equal to minus u0 times theta, which theta we had defined as the momentum integral thickness in the last class. Okay. Now, based on this, what can you say about us times L? These are the only things which are functions of x. This is a definite integral, it is a number. u0 is a constant, does not depend on x. So, therefore, what can we say about us times L? This means us multiplied by L should not depend on x. Why? Because m is not a function of x. Okay, because here the only things which depend on x are us and L. So, therefore, this product should be independent of x. Is that clear?
Yes.
So then n would be 100.
So, now then we will work it out what is n. Okay, this is the second condition, and this is how we use the second condition. So, this gives us that us times L, this because now m is independent of x, and this implies us times L must be independent of x, because that is the only thing which is coming here. Now we have L is x to the power of n, us is x to the power of n minus 1. So L times us is equal to x to the power of 2n minus 1, and this implies 2n minus 1 must be equal to 0. So n must be equal to half. Okay? And see, this is the whole exercise which is being done to get the function of us and L as a function of x. So again, two things to be used. One is the equation. In equation, when we compare, we get one equation, and the second equation comes from the boundary condition. In some sense, you can call m being independent of x as a boundary condition or an integral condition. So the second thing always will come from the boundary condition, because the boundary condition is what defines the flow. In many flows, the equations are the same. So if equations are the same, the first condition may come out to be the same for many flows. But the second one is specific to that class of flows. For example, for jets and wakes, we showed that m is independent of x. This is not there for mixing layers. So there we'll have to see something else will have to come. Okay? So n becomes equal to half. So based on this, what I can write is, this tells me then, therefore, us goes like a times x to the power of minus half, and L goes like b times x to the power of half. Now this is the condition for self-similarity of the plane wake. This may not exist. This is just what the equations are telling you. So in real life, it may not exist. We have found out that, okay, if the wake has to be self-preserving, it has to follow this. But this does not mean it has to exist in real life. And the other thing which may happen, which happens in a lot of turbulent flows, is, or may be unstable. There may be more solutions for capital US and L, and this solution is unstable. What do you mean by unstable solution? That while the solution theoretically exists, but if it is disturbed from this, it goes to some other solution, which is probably not a self-preserving solution. A self-preserving solution has to be of this form. If it has to be a power law in X, then it has to be like this for it to be self-preserving. But maybe it just doesn't follow this. It is a general function of X and Y. We cannot get this solution. So that could also happen, but this is the, so now how do you check this? So we need experimental evidence to check this. No, there are numerical ways that you check the stability of the equations, and you apply concepts of linear stability, hydrodynamic stability, and that could also be done. Yeah, that could possibly be done to check this, but we need experimental evidence to check. And what we find is, the experimental findings are, beyond x is equal to 80 times the diameter of the body, these solutions exist for a plane wake. The velocity fluctuations u prime, v prime, they generally show self-preservation beyond x is equal to 200d. So they require some more distance downstream before u prime v prime or the Reynolds stresses become self-similar. Okay? And in fact, if for higher order turbulent quantities, like v prime cube, v prime 4, etc., we need something like 500d. Now let us try to find no, I've just talked about the RMS u prime, RMS of v prime. So when I say here u prime v prime, I should say RMS of RMS values of u prime and v prime. Hey, u prime RMS. U prime RMS, we are using it as a special meaning for order of magnitude. But this means the RMS of u prime. Okay. No, for u prime, so about 200 d pe you will find the Reynolds stress goes self-similar.
So the correlation.
U prime v prime. That means for us to have u prime v prime upon us square is equal to g of zeta. We need to travel about 200 d from the body. Otherwise, it's still evolving. And now what we do is for the mean velocity profile, let's try to find this. So to find the mean velocity profile, we put us is equal to a times x to the power of minus half, and L is b times x to the power of half in the equation. Now first let's write our equation. Equation was minus u0 L upon us square dus by dx times f plus u0 upon us dl upon dx zeta f prime is equal to g prime. This was our equation. So now we put in us, we'll put a x to the power of minus half and L as b x to the power of half. So when you put this in, okay, so dus by dx will become what? It will become minus half times a times x to the power of minus 3 by 2. Okay, there's a us square here also, and then u0 L, u0 will just stay as u0, and then us here again you will put ax to the power of minus half, then there's a dl by dx, so that will become half b times x to the power of minus half, and then rest will stay the same. So you put this in, and I am not doing this thing. Finally, this will lead to, and this you'll have to probably check at home, half of u0b upon a. This term comes out as a constant. All the x's obviously will have to go away, times zeta f prime plus f is equal to g prime. Now there are two functions f and g. F represents what? The mean velocity or the defect in the mean velocity. Keep that in mind. What is g? g क्या है देखो क्या है नहीं क्या है जी एक मिनट देखो जी हमने कैसे डिफाइन किया है नहीं जी क्या है जी एक फंक्शन है हाँ u prime v prime तो g represents the Reynolds stresses, a non-dimensional Reynolds stress. F represents the velocity defect, appropriately non-dimensionalized and with some other coefficients वगैरह जो भी, but effectively keep that in mind that f is the mean velocity. u0 minus u, and g is the Reynolds stress, u prime v prime. So now f is the mean velocity, g is the Reynolds stress. So we still need some relation, and here now we need a relation between f and g. F is the mean velocity profile effectively, and in suitable form, and g is the Reynolds stress. In, again I'll use the word suitable form, is probably not the right word, in some form I should say, probably suitable bhi nahi, in some form. Now, is there some relation we have which relates the Reynolds stress to the mean velocity, or do we use some empirical relation to relate the Reynolds stress to the mean velocity or its derivative? How do we do that? We हाँ नहीं, पर कैसे हम, मतलब ये what did he say? But what approximation? Boussinesq. But what is Boussinesq approximation? What does it define? Right? Eddy viscosity. So the way we define eddy viscosity, we say Reynolds stress is equal to eddy viscosity times du by dy. That is how we have defined eddy viscosity. So that is what we do here now. So we define nu t for the eddy viscosity is defined such that minus u prime v prime is equal to nu t times du by dy. Now, this when I put in, what I will give me is, this will lead to nu t is equal to minus us L times g divided by f prime. So basically, how do I get this? Nu t will be equal to du by dy minus, nu t will be equal to minus u prime v prime divided by du by dy. So write u prime v prime as g times us square, and du by dy, go write it as du by d zeta times d zeta by dy, and that is what is going to give you this, because du by dy is going to give you f prime. Okay, so this is coming from here. So nu t can be written as minus us times lg times this. So from here what we get is, this is the relation nu t divided by us times L is some function is equal to nu t divided by, not is equal to g by f prime, sorry, is, let's first write it, nu t divided by USL is equal to g nu t divided by US. एक मिनट में मिटा देता हूँ इसको. Now nu t divided by US of L is equal to minus g divided by f prime, and this is a function of Now, G is the Reynolds stress. So, Reynolds stress profile we know is symmetric about y is equal to 0. Okay, it will be the same. Similarly, f prime, which is the derivative of mean velocity, this is also symmetric about y is equal to 0. So, this tells us that this function which we have nu t and us times L does not depend on x, that is a constant. We have shown that. So, nu t itself will be a symmetric function. Symmetric function means whatever is its value at y is equal to a, at y is equal to minus a, it will have the same value. So, it will be something like this, and what we are, then think of this wake. So, if you look at this wake, in this region, this is all mixed up very well. This is a turbulent flow, it is mixed up. So, if it is mixed up, then what we will expect is that this value of nu t in the region close to the center line will be almost a constant, because it is a function of the velocity scale here multiplied by the length scale here. So, this nu t, what we are doing here is this nu t, because this is, so first G and F are symmetric functions, so this implies that nu t is symmetric, and we assume it is approximately constant near the wake center line. And a physical reason for this is nu t goes like u prime times L, and since flow is well mixed near the center line, we expect nu t to be constant. Now, a peculiar problem comes that G and F prime are nu t is given by G divided by F prime, and at the center line, well, it says G and F prime are both 0. So, is nu t finite? And we have limit y going to 0 G by F prime, and here to find this value as y goes to 0, we use L'Hopital's rule, which means that this limit will be equal to G prime upon F double prime at 0. And F double prime at 0 is not equal to 0. F double prime is d2u by dy square, and this is finite. So, therefore, this limit will exist. It will be a finite. This is just, I think I am going too much in the detail, but just to show that it could be possible. So, it's just a sort of corollary, you can think of it. And based on this, what we get is nu t upon us of L This we define as 1 over RET, and RET we say is the turbulent Reynolds number. Yeah, we are just saying that. So no, it no, but it no. So see, the denominator is constant as long as the numerator again is not 0, g double prime. So it will be a finite limit. It is not something that it will blow up to infinity.
So I think I think the initial
Ah.
question
Was
is notified,
uh,
but we cannot talk about the triviality of nucleus.
triviality in what
In
sense?
the sense that is it zero or non-zero, we cannot talk about that.
We cannot, but it's a but it's not blowing up. It's not going up to infinity. Now, so therefore, what we are getting from here is basically, again, we have made this assumption that nu t is equal to constant. So there are too many assumptions being made. But now, what one can do is, we can now put this in the equation. So our equation will become half u0 b upon a times zeta f prime plus f, and this is equal to minus 1 over RET times f double prime. So basically what we have got is a single differential equation for f. G we wrote in terms of f, basically by using the eddy viscosity approximation. So what we have got is an equation for mean velocity. Okay. So this gives us this equation for mean velocity, and now what I can do is I can just take everything. So this becomes equal to half times RET u0 b upon a times zeta f prime plus f double prime is equal to 0. And we can define this whole constant half RET u0 b upon a, all of which are constant. We can call this as alpha. So our equation becomes alpha zeta f prime plus alpha f plus f double prime is equal to 0. This is an equation in f, in the mean velocity.
So is there a reason that you have specifically said it is turbulent Reynolds number?
Because we are defining it in terms of nu t, not nu. So that is why. I have not used nu here, I have used nu t. When I say RET, I am not using nu, I am using nu t. That's why I am calling it as RE turbulent. Otherwise, in general Reynolds number, we always take nu of the fluid. But यहाँ RET use किया है तो nu t use किया है. That is the sort of. Now this is a differential equation. F is a function of zeta, and it turns out, I'll just give you the, will not, in fact even I am not very sure how the solution comes out, but if you put f is equal to exponential of minus half alpha zeta square. Alpha is a constant. If you put f is equal to minus half exponential of minus half alpha zeta square. So then what you do is you find f prime. What is f prime? Iska derivative. So minus half alpha times 2 zeta times the same exponential. And then f double prime. And then you substitute it in this equation. that is what you will show that it becomes equal to 0 if this is the right solution. And so here we are just, I'm not showing you how this form comes. We are just putting this form, and when we put this in, we get it like this.
Can this come in the exam to get the solution to this?
मैं खुद ही नहीं, मुझे आता तो मैं तुम्हें क्या पूछूंगा. I was thinking, I was trying to derive it hard. I just see, normally in cases like this, what happens is because of this alpha zeta in front of f prime, you will get a zeta square term. See, normally these solutions of this type, they go like f is equal to exponential of a zeta or exponential of some constant times zeta. You feed that in the equation and you get some sort of an equation. Maybe you can try to get it.
Just one more doubt, like there should be actually two solutions to this, right? Like generally, so when you are writing a general solution, you either say that one solution is a e to the power like zeta and a b e to the power minus
So
zeta,
the,
or you can have a general solution and a particular solution.
नहीं particular तो इसलिए नहीं होगा क्योंकि left hand side, right hand side is 0.
Right.
So there is no particular solution. Now general solution, because it's a second order differential equation, possibly there will be two solutions.
So maybe what is happening is the one with the positive coefficient, like it's pre-exponential is 0.
Something like that is happening, probably because we have not even put in the boundary conditions here. When you probably put in the boundary conditions, then you get this form of f. So
Only the pre-exponential of this one.
तो इसका I don't know. अगर if there are some experts in maths, why don't you try to find the solution, how to get this solution?
So what are the boundary conditions that you put here?
Boundary condition तो u पे mean of u की लगानी पड़ेगी. तो one is on the at y is equal to 0, this will be 0, the derivative f prime. और the दूसरी boundary condition probably will come from that again, the integral condition, momentum equation or something that is not a, already m is not a function of x is already here. So anywhere, ठीक है, I think I'm finishing. So कल क्या, कल सैटरडे, कल क्या है? आज का फॉलो होगा, आ गया है नोटिस? हाँ, कैलेंडर में है तो ठीक है, देन वी विल टीच फ्रॉम कल. फिर पढ़ाना है ना, कल पढ़ाते हैं क्योंकि एक क्लास मेरी मिस हो गई थी. तो टुमारो देन वी विल मीट एज पर रेगुलर शेड्यूल. हाँ, क्लासेस असाइनमेंट देने हैं, मैं कल तक बना देता हूँ एक. मैं असल में इसका एक वो असल में इक्वेशंस में नहीं लिख पाया, इसीलिए मैंने नहीं बनाया. If we do a similar exercise for a axisymmetric flow, we will get different values of n and n minus 1. तो I want you to do that. तो उसका मैं पर उसको मैं इस तरह से बनाना चाहता हूँ कि तुम लोग that I give you enough hints to solve that. तो I'll make that problem today and give it to you.
That will be question.